the honor for us that we have the next speaker, and I would like to thank him for his time to be present to this winter school. Is Professor Auricchio from University of Pavia. He's a leading expert in computational methods in mechanics and in additive manufacturing simulations. And I would say that he is the president of European Community of Computational Mechanics, ECOMAS, from last year. So, Professor Auricchio, please.
So, good afternoon to everyone, and thank you very much for the presentation and for inviting me here to address this lecture. I hope that you can see my slides, right?
Yes.
Okay, great. So I'm going to concentrate on simulation for additive manufacturing, and I think that additive manufacturing is really a world of opportunities and at the same time challenges. I'm sure you already saw many of those, but I would like to highlight few extra opportunities and challenges. So since the school is on additive manufacturing, and I don't think I really need to go into it because you are expert by now, and I will really focus on different areas of simulations and possible activities you can do with simulations. So, you know, additive manufacturing, and the point I want to make are basically two. On one end, additive manufacturing is a wonderful technology because you can easily produce complex geometries. And in many cases, you can also you can put multiple components in a single device. So it's very easy when you deal with additive manufacturing that you end up with components, with objects which are really, which have a really complex geometry. On the other hand, so that's the good news. The bad news is that when you talk about additive manufacturing, you're always talking about production process which are very localized. They are production process with a very high gradient. And in this respect, you know, computer simulations are extremely important. So the idea is to address different opportunities. And I will start talking about design for additive. Design for additive presents several challenges, and one of the reasons is that basically additive manufacturing is really opening your brain, and you can dream any sort of geometrical complexity. So you're very close to freeform components. And this means that if you really want to take advantages of these freeform possibility, you really need to optimize your geometry. And this brings our attention to topology and shape optimization as extremely important tools for the design of these components. So topology optimization is something that you already saw in the course. The idea of topology optimization is basically that you have a domain in which you want to distribute a certain amount of material, and you want to optimize the distribution of these materials in order, for example, to minimize the structural compliance. So you have your domain, omega, you have some boundary conditions, some loading conditions, and you want to distribute some materials and minimize, you know, some functional. Our approach is to try to minimize, for example, the compliance using phase field method. This is a method which does not require any filter like other methods, and it's very nice because you can get some mathematical proofs regarding the convergence of the method, and these also transfer, you know, these features also in some numerical aspects. So the idea is to solve equilibrium, at the same time minimizing structural compliance, and our idea is to do everything trying to work not you know, with a graded structure, so with a structure with varying density. So we introduce in our model two phase field variables. The first phase field variable is the phi, and basically this phase field describe material presence. And then we have another phase field variable, the key, which describe material feature. So with this new variable, with this second variable, basically we want to give the opportunities to our structure not to be to show only one structure, one materials, but we want to have inside our domain the possibility of going from a material B to a material A. And that this is really related to the fact that with additive manufacturing, you can easily produce like microstructure or lattice structures. So the idea is that you don't only want to understand where you don't need to put the materials, and that's the phi variable, but you also want to describe which materials you want to place and where. Okay, so using a phase field approach, we introduce a functional where you have your standard compliance, which are basically the two integrals reported here, and then we have also a very classical measure of the perimeter, which is associated with your first variable. However, since we have a second variable, we also want to penalize the gradient of the second scalar field. So basically, we don't want to have the possibility of a structure where you jump from material A to material B too many times. So we penalize this other gradient of the second scalar variable through a parameter that we call k key, okay? And to this function, we also add the very standard constraint on the amount of the material that we distribute inside our domain. So this is a very classical approach, except for the term that's bounded here in the yellow box. And clearly, we want to penalize, we want to minimize this functional, satisfying at the same time equilibrium. Clearly, we're very much interested into computational aspects, so we solve our problem introducing an Allen-Kahn gradient flow. So we introduce a sort of evolutionary solution algorithm where you can see that you solve incrementally the first phase field variable and the second phase field variable. And we develop a two-step algorithm. So the two-step algorithm, basically there is one step in which we solve equilibrium and another step in which we progressively solve the gradient flow and update our phase field variable. Clearly, you can then discretizing using finite elements, and the very nice thing are basically the example you can produce. For example, this is a very standard problem. So this is a cantilever beam, which is clamped on this side. You have some distributed load here, no body load. And if you make your tool, your numerical tool running, at the end of the story, you can get this type of solution. In this type of solution, which I think are quite interesting, basically gray, the color gray up here and here on the left means no material. So the gray regions means that you don't have to put any material there. The colors, the other color except gray, instead means different material. So basically you can see that in the red area and in this part here, you have different materials. So the structure that we obtain through these topology optimization schemes is already a structure with a gradient, which you can easily produce with additive manufacturing. The very nice thing is that you can clearly change your parameters in your model. And depending, for example, on this parameter gamma key, you can obtain different structures. So if you really increase on this parameter, you will obtain a structure with a single material, which is the classical result from topology optimization. But if you relax the constraint on the gradient of key, you can obtain a solution like this where you have basically graded material. You can clearly do parametric studies, and here I'm reporting some numerical results. And really, to go, to the basic concept is that changing, the constraint on this second field, you can obtain a structure which show different compliance, but at the same time also different weights. And you can go from, you know, a single material structure to a structure which really expose this gradient material inside it. So you can really, you have another extra degrees of freedom in your design, which we believe it's quite useful. Okay, you can do exactly the same thing, for example, for other type of problems. So I was showing, you know, the first result for a cantilever beam. Here you can see a very standard comparison test, which is, you know, this type of simply supported beam with a concentrate load in the middle. And if you run your optimization, you can see with the black color now the region where you have material or you don't have material, and with all the graded color here, the region with different type of materials. And the very nice thing with additive manufacturing is that you can also produce your component and you can do experimental tests. So once we run our numerics, we also develop some computational steps in order to end up with a component, which you can see here, where you can a little bit see the internal structure. So you can see that in certain region you don't have the material, but in other regions we have, you know, a graded structure. And the very nice thing is that we did experiments, and basically here on the right you can see the structure which is uniform as a material. So we distributed uniform a certain amount of material, and on the left instead we see the same, you know, the same geometry, but where we distributed the same amount of material. So this structure on the left, so the structure on the left and the structure on the right have the same amount of material, but on the right is uniformly distributed. On the left is distributed in, you know, in a graded way. And here are the mechanical response. And clearly you can see, for example, that, you know, for the same amount of material, for the same amount of load, for example, the structure which has been properly designed, you know, behaves much better, is much stiffer than the other structure. So distributing in a smart way your material inside your domain can really have an effect on the performance of your component or device, okay? The first two examples I show you are two-dimensional examples, but clearly you can run the same algorithm in 3D, and here you can see some initial results in 3D, but, you know, we are getting new results also in these days. So basically the tools work properly also in 3D. One of the problems that you encounter when you study topology optimizations, you know, with such a freedom, with the freedom that you can have with the additive manufacturing, is that you don't know exactly where is the region where you need to put the material. So the idea is to start, so if this is the domain where you want to distribute your material, the idea is to start with a very uniform numerical grid, but also to develop adaptive, sort of adaptivity schemes to obtain refinement and also to capture, you know, really the local structures. Okay, so since basically you don't know where you're going to have material, where you're not going to have material, the idea is that either you have a very fine mesh from the beginning, or you start with a crude mesh from the beginning, but then you need to have local adaptivity. And here you can see some results, some very interesting results, where we combine adaptivity and isogeometric approximation schemes, okay? On topology optimization, we are also looking at other aspects. And here, basically, we are proposing several advancements. One of the things is that referring to the previous formulation, now we look at the single material. So we do in a certain sense a step back. So we don't look anymore at the graded material structures, but we look at the single material structures. And we consider the very standard volume constraint formulation. The nice thing is that we try to include in our functional not only the compliance, this I, which is already the compliance, you know, you saw before, but we try to include a bunch of different terms which are able to enforce directly from a functional point of view also equilibrium. In the previous approach, basically, I was minimizing compliance on one end with the control of the field variables, and then I was imposing equilibrium, but I was not really enforcing the two things together. Now, with this functional, we enforce everything together, okay? So we enforce the minimization of the compliance, but we enforce also other constraints, and in particular, equilibrium, adopting something like a Uva-Shizu approach, and then clearly we also add volume constraint. What is the beauty of this approach is that since everything is one functional, we can very easily forget the algorithm I was showing you before, because previously I mentioned you that we were updating, we had the multiple step algorithm. So in one step we were enforcing equilibrium, and then the other step we were enforcing the update of the internal the phase field variables. With this functional, you can very easily explore monolithic solution schemes which possibly have a better behavior. Okay, so this formulation is very interesting because you don't only enforce volume constraint, but you enforce minimization of your compliance and equilibrium just in one box. Okay. At the same time, we also feel that this formulation with volume constraint, which is very classical in the topology optimization literature, in some sense is missing a little bit of engineering feeling. And in fact, our approach is that we don't really want to distribute in the domain a certain amount of material, but we want to minimize the material that we distribute. So we come up with another formulation, which is down here, where you can see that the first part is identical to the previous one. So we minimize the compliance, we enforce in one-shot equilibrium, but now we don't impose volume constraint, but we impose a volume minimization. So we have a very standard volume constraint formulation, a very classical one, and then now we have a new formulation, which is a volume minimization formulation. And the nice thing is that basically you can run your simulation and you can show that basically volume constraint and volume minimization approach in some sense obtain, you see the two curves are identical, which means that with the two formulation you can obtain basically the same results, with the difference that in volume minimization you automatically in some sense also minimize the material you put in your formulations. But the very nice thing is down here, where we plot convergence versus the, let's say, simulation time. And the red curve is much more, let's say, uniform than the blue curve. And the blue curve is the volume constraint approach, the classical approach, while the red curve is our approach. And so this new formulation seems to behave much better from a numerical point of view. And you can see the results also here, where basically we have the number of iterations, and basically with the red approach, so with the volume minimization, easily we get less number of Newton iteration to obtain our solution. Okay. Okay. So this close the first thing the first message, which is designed for additive, which is basically trying to find the best way to distribute your material in the domain. And now I will move to the second area, which is slightly different, and it's process simulation. So additive manufacturing is not only, as I was mentioning at the beginning, is not only giving you a lot of freedom, so you need to look at topology optimization, but it's also giving you a lot of problems, because it's a very localized, non-linear phenomena that you use to build your component. So to produce object with additive manufacturing sometimes is not as easy as to produce from the technological point of view as with the standard technologies. So you really need to do computer simulation and try to support your construction process with the simulation. What are the challenges when you want to simulate the process simulations? there are many different challenges. One is the large scale range, because the process is local, is in a range, is in a very small range, so it's very, very, very local, but you want to construct components which are very large. So you want to describe at the same time very different scales. And then on the other hand, you want to describe very complex physical phenomena, okay? So it's really computationally challenging. So on one end, the classical approach is to use, a very iterative loop, which is the standard design process. So basically what you do classically, you draw your component, you mesh it, and then you do the simulation. And if something is not really working, you go back. And this process is really iterative and it's really time consuming. Our idea is to try to be much faster, so not make this iterative process so rich in terms of steps. And the basic idea is to try to use directly your CAD model to perform analysis. So we don't want to mesh really the geometry, but we want to use directly the CAD model to do the analysis, okay? So the way we do this is using immersed method. So in the following, I'm going to talk about two different immersed technologies. So the immersed technologies conceptually is very simple. So if you want to study a component of this with this geometry, you simply immerse your physical domain in a much larger domain, and basically you mesh the much larger domain. So your mesh is not, as usually said, is not a fitted mesh. So your mesh, so if this is the physical component, your mesh is not following the boundary of your component. So the mesh is somehow independent of your component. So you have a very large domain which you mesh it, which is going to be your computational domain, and then you take your component and you project your component or your computational mesh without, let's say, paying any attention. What is the problem? The problem is that the mesh is not fitting. So you need to take care. You need to somehow describe where is your component and where is not your component. And to do so, you have some sort of local refinement. So you progressively, so if you take a region down here or a region here up here, you progressively refine locally your description, and you take into account the geometry not through a conforming mesh, but through a conforming integration rule, okay? So you don't refine the mesh, you refine locally the integration points. So you put more and more integration points in order to describe properly your geometry. Okay, so this is the standard immersed method. In particular, we are going to look at the final cell method, but beside that, we combine the classical final cell method with another ingredient, because basically what happens is that the dimension of the final element that maybe you introduce is not so small to really describe the process of lay down, for example, powder, and melting the powder and then describing the solidification process. So we also introduce, let's say, Gauss integration refinement in order to describe the progressive deposition of layers, okay? So we need to distinguish between the cell, the cell dimension, which is basically the dimension of the final element mesh, and the powder layer dimensions. So we really need to distinguish between the physical ingredients and the computational ingredients. But this approach is extremely flexible, and in fact, using this approach, we were able to describe melt pool, to perform a melt pool analysis, which we also name it as high fidelity simulations, and part scale analysis, which are clearly much lower fidelity simulations. And the idea, in any case, is either to describe locally what's happening or to get a very global response. And here there is a very nice movie that I want to show you with you. This is a plate that we 3D printed in our lab, and you can see that the plate basically is so rich of components that it broke the screw that were used to hold the plate to the machines, and now the plate is even bended and it can, you know, rotate on a table. So this is really something you don't want to happen during your production process. So you want to simulate this behavior and try to avoid this type of behavior. So the question is, how can we simulate melt pool investigations or part scale investigation using this finite cell method? So here is the melt pool description. Clearly we have a thermal part, we have a mechanical part. In general, we try to use very simple models, because if we put too many ingredients in the model, we don't, you know, the computational burden will become too high, and we are not able really to get the numerical simulation to run. So we have a very simple thermal model where basically we describe phase transition in a very approximated way, and then we couple the numerical thermal results with our mechanical system, and here you can see the simulation of a thermal problem where basically you see a laser moving back and forth on your component, and here you can see on a different geometry the mechanical counterpart. Okay, here you can see in reality multiple laser path and multiple layer powder layer depositions. Okay, so the idea is to really get to very simple models, but clearly we want our model to be feasible and accurate. And here I'm showing you some very interesting results performed against experimental results producing during the additive manufacturing bench in 2018. And for example, you can see here some ex situ measurements of the melt pool cross section. So there were some run of your laser, and then the component was taken and cutted, and you can see the numerical result with the red curve and also the experimental data. You can see that, you know, there are some differences, but there is a very good match between the prediction and the experiments. And you can see also, you know, some in situ measurements of the melt pool length. And here you can see on the left the measured melt pool, on the right the model melt pool, and, you know, there is a good match between prediction and experiments. And using this technology, clearly you can do always more and more complex things. And here you can see some results relative to current investigation on different scan strategies. So basically, once you have a numerical tool that's able to accurately predict what's happening in the material, you can start also to design, for example, your laser scan pattern in terms of powder and speed, and try to optimize, you know, what's happening in the material. And again, you can see here some, you know, different numerical investigations, and, you know, we are trying to match with also experimental data, but, you know, results seems to be very interesting and in the right directions. So this is everything at the low scale melt pool, but we also were also very much interested in what's happening at the high scale. At the high scale, and the high scale, so the component scale, we also have a thermal model and a mechanical model. Again, very simple. And we combine the model again to run together. And let me go directly to some simulation. This is a very simple, you know, very not simple, but very classical simulation. Is the bridge where we progressively simulate the deposition, the heating up, and the mechanical response, and, you know, also the cutting of the structure from the base plate. And here you can see some comparison between numerical results and experimental data with a very good match between the experiment and the numeric. So I think, you know, the tool seems to be quite effective. Clearly, the finite cell method is not only the only immerse method you can think of, but there are also many other methods. And here, for example, there is another two-level method where basically we do a different approach. We don't refine using Gauss points, but we refine locally the description through a local small finite element mesh. Okay, so basically, so we have a background mesh, we have a global background mesh which is fixed. We have a region where the represent the component which is building up. So there is a region which is the physical region and the region which is going to be built, and then in the sub region where really the physics is happening, we put also an extra local very fine local mesh. Okay, so here the idea, I'm showing you, just some simple ingredients. For example, for a very simple toy problem, let's say just a thermal problem. So the idea is that if you have a thermal problem in a certain domain, for example, with an inclusion, basically you split your thermal problem in this domain with an inclusion in a global problem which does not see the inclusion, and a local problem which see the inclusion. Okay, so instead of solving the problem in the domain A and in the domain B, taking into account the different mechanical properties of the two regions, you solve the problem in a global domain and then in a local domain. And you can develop numerical tools where basically you solve first the problem locally, then globally, and then you iterate between global and local, and you get convergence to the right solutions. Okay, and here, for example, I'm showing a very simple example, again just a thermal. So you have a domain like this one. So the lower part is the domain omega A, the upper part is domain omega B, and we split our problem in a global problem, which is the whole domain, plus this very, very local region. And we assume that only in this local region we have highly non-linear phenomena. The very nice things from the numerical point of view is reported in this picture. What is showing this picture? It's showing, the fact that if you basically, if you fix your global mesh and you refine only locally the mesh, okay, so you fix the mesh on this domain and you refine the mesh only here, you see that you get always a better behavior. So basically, if you have phenomena which are very local and you want to describe better and better this phenomena, you don't need to refine the mesh everywhere, but you need to refine the mesh only in the local region, okay? And that's what's showing these numerical results. And clearly you can try to do everything also not on a fixed domain, but also on a domain that's evolving. And here on the left, you can see some preliminary results which show the temperature profile, which increase progressively because it's the laser that's turned on and off. And on the right, you can see that the component is progressively building up. Okay. So this closes the second part of my presentation, which is on process simulation. So basically, the ability to really take into account either very local phenomena at the melt pool scale level, or to really support the design of the complete part, describing, also the production, for example, of residual stresses. And I was showing these in this second part using immersed technology. As third part of my presentation, I would like to discuss with you a third part where simulation can be extremely important in additive manufacturing, and it is product simulation. What is the challenges for product simulation? You have many different challenges, and basically the main challenges are quality control of the final parts, material characterization, and try to really understand the mechanical properties of the printed part. So this third area of contribution is really an area where you really produce a component and then something goes wrong and you don't understand why it's going wrong. And so the question is how you can support your design through computational. So here I'm showing two different areas of activities. One is relative to lattice structures. So everyone is trying to, everyone that's using additive manufacturing is really into producing lattice structures, but you know, lattice structures are very nice because they can make your component very light, but are also you know, really problematic from many other points of view. And the point of view I want to show you is that basically the dimension of the lattice, usually it's very close to the dimension of the precision. I mean, it's very close to the precision of the technology that you use to produce your component. And this can be extremely challenging from a computational point of view. And in fact, what is the experience we did? Basically, we 3D printed some lattice. We did some experimental campaign, so we get some force displacement curve, and then taking the geometry of the lattice, we ran some simulations, and we were getting, you know, from experiments and from physical experiment and numerical experiments, we were getting very different results. So the mechanical behavior was far away from the predicted behavior. And one of the reasons is really, if you really do, for example, if you do the CT scan of your component, is that since your lattice structure are very, very small and you try to make it as small as possible, so you get very close to the production precision, at the end of the story, your lattice structure is extremely irregular, okay? So here you can see CT images of our lattice structures, and you can see easily that, I mean, it's completely far away from the idealized CAD component that we design. So not only we have a very different structures, but now that we have this structure, the point is, how can we do computational with these structures? Because you can see that this geometry is extremely complex. So the idea here is, again, to go toward immersed technology. And so if you immerse if you immerse your CT scan images inside a much larger domain, and you iterate with and you describe your geometry with the refinement on Gauss points, and run experiments and now do the simulations, you can get a much better response. And you can see here the comparison. Let's look just at this, for example, these last results. So you can see here with this column, the experimental value. With this other column, you can see the numerics obtained adopting as a base for the numerical simulation, the idealized geometry. And as I was mentioning you before, these results are much different than the experimental results. So they make, I mean, the two structures are completely different. But if you use the really the really produced geometry, so the CT scan based geometry, you get a very good match between numerics and experiment. So lattice structures can be really problematic, and advanced computational tools can be really effective. But in terms of industrial support, another area where that's really opening a lot of different activities is, you know, supporting companies really in the production of components. And here I'm showing you here some experiments that we are doing with different companies, in particular with the coffee machine producer that's named La Marzocco. And here you can see a component of the coffee machine. It basically is the part where you really put coffee powder. And here you can see instead a decorative component. It looks like Florence lilium. And these two components have, you know, really pose us some very interesting questions. So for the powder, so for the filter support, the idea was to really optimize the geometry, because they want to have geometry which was able to increase the temperature of the coffee powder. So with additive manufacturing, it was possible to very quickly come up with the numerical simulation and do the production of the components, and also do the experiments. So we really tested our new design on the coffee machine, and we were able to, you know, increase the temperature. So in order to really do the optimization process and the production, you know, you need to also do a lot of simulations. But this is a very interesting area. Or another area where computer simulations, you know, are very useful is that sometimes when you produce your component, you get defects, which are basically related to some of the things we already saw. Here you can see the idealized Lily geometry, but once we produce it, we got, you know, a very funny response. So there was a very clear anomalous misalignment in the production process. So we did we performed the numerical simulation, we corrected the geometry thanks to the predicted residual stresses, and then we were able to change the shape of the printing design, and we reprinted the component. And as you can see here on the right, the new component, which is the correct one, is much better than the previous one. So has no defect, okay? Clearly, as I was mentioning you before, additive manufacturing is a very challenging area for many computational aspects, but it's also extremely interesting because it's opening always many new ideas, many new areas of activities. Here I'm showing you two areas where we are very active at Pavia, which is the designing of new 3D printing technology. For example, here you can see some gel-based deposition technology, let's say some sort of FDM, which basically, however, are components that need to go through a sintering process. And again, the idea is that the computer simulation can really support this technology, because, I mean, this is a very complex technology because you need to describe computationally all the sintering process. And here you can see another technology on which we are working, where basically we deposit powder, and we also have a sintering process, and simulations can be also extremely useful and important in order to optimize your component. But again, you know, 3D printing is really opening many areas of activity. So here I'm showing you some of the other areas of activities in which we are working very hard in Pavia. So, for example, we have a very interesting lab in the hospital where we support surgery, and there are many computational challenges because we want to obtain reproduction of organs which are as close as possible to the real organs. So there are many mechanical questions and computational issues. Another area of activities is bioprinting. So printing gels with cells. And here there are many different physics that needs to be described in order to try to understand why how cells behaves. But also, you know, there are many activities on 3D printing of concrete, which is extremely interesting and challenging, and also the 3D printing of active components, possibly with multiple steps. So really smart component, and this really brings, you know, to the closure of my presentation, of my quick excursus. And in order to come really to conclusion, the only conclusion I can do is that everything I show you clearly, you know, I was presenting, but it comes from the work of many people. So let me thank you in particular Massimo Carraturo, Stefania Marconi, Gianluca Laimo, Alessandro Reali, Michele Conti, and Simone Organti, who are in Pavia. As I was showing you in the presentation, I didn't mention the names, but we have also many international collaboration. But I need to in Pavia recognize the work of these 7 co-workers, but clearly there is all the team that's always worked in this area. And so I hope, in conclusion, that I really also show you the 3D printing is really challenging, but a breakthrough technology. So I hope that, you know, many of you want to challenge themselves in computational mechanics within additive manufacturing. Thank you very much.
Thank you. Thank you very much. Very nice presentation. If there are any questions. So again, thank you very much for your presentation. Sorry?
Maybe I'm still, my name is Angel Cernescu.
Nice to meet you.
I'm still thinking to the test that you show us in the beginning of the presentation, where there was a bending test on a optimized component.
Mm-hmm.
And it was a bending test that you show. Yeah, this one.
Yeah.
So how did this fail during the test?
Okay, we didn't really explore the failing. I mean, the goal of this test, I was really quick. I show you many things, but this is a very interesting experiment. It's somehow standard now in 3D printing. So on the right, we have a beam. So we fix the domain and we say, okay, let's put in this domain, like, I don't know, 70% of material. So we decide the amount of material we want to distribute, but we distribute uniformly. So in all the points, we have a little bit of voids and a little bit of non-voids, okay? So this beam is uniformly distributed in your domain.
Yes.
On the left, instead, we use this graded technology. So on the left, we have area where we have a very dense material and area where we have much less dense material. And in fact, you have regions, for example, here on the support where the geometry is really fancy. So we have regions where there is no material. Here, for example, in the middle, there is even, you know, less material.
But how can be the material more dense in some region?
Well, with voids.
In the same volume, in the same.
No,
volume.
you can do with the, let's say with lattice, for example. Or let me show you. Maybe at here.
It's not fully filled.
Exactly. So for example, here, you see, so I can have the same structures, which is really more voids than material or much more material than voids. So I can, even if I fix my lattice geometry, I can put for unit volume, I can put more or less material. And so in the structure on the left here, I distribute non-uniformly the density, and on the structure on the right, I distribute uniformly the density. And I obtain on the left a much stiffer structure.
Okay. And where is this less the density material distributed in the left side? On the left.
You can see this picture. If you look at this picture,
okay.
So the high density is on the support and basically in the bending in the middle.
Okay.
And for example, you don't have much of material here or here. So if you look at the pattern, you can recognize where is more dense and where is less dense. So the red is more dense.
Okay. And the red region means material with a high degree of porosity.
With full porosity, with the full density. Green means low density. So low density
yes,
here
green,
and in the middle here.
Yeah, in the green region, there is material with high porosity.
Exactly.
Okay.
And clearly this is a very simple problem because we talk only of density. You can clearly work with computational tools where you have also, for example, orthotropy. So it's not only having density, but you can also decide, okay, I want to have lattice, but I want to change also the orthotropy of the lattice. For example, I can make, you know, my square lattice longer in one direction or longer in another direction in order to go to orthotropy or anisotropy. So additive manufacturing is really giving you so much freedom to do design that you can use it if you want to.
Okay, yeah. Now I understood. You know, it's clear for me.
In any case, you know, I was really fast on you know, I jumped between many different topics and technologies. But clearly, for any question, you can send me an email, and I will be happy to interact, you know, and give insights or papers or discuss it, because really it was, you know, quick. I don't think that computational tools were really the focus of the school. I'm not sure, but you know, if there are questions.
Yes. Yeah, maybe this discussion is an open one, because now I'm thinking if you
Angel, we have another activity scheduled. So
sorry. Yes, I'm
you
sorry.
you can send an email to Professor
Yes.
and discuss further.
Yes, please do it. Yeah.
Yeah. Okay. I thank you very much again for your presentation. Thank you.
Thank you very
Yes,
much.
thank you very much.
Bye.
Bye.